Neptune sits at the very edge of the solar system, farther from the Sun than almost anything humanity has ever visited. From Earth, it looked calm, beautiful, blue, a frozen jewel floating in darkness. But that image is a lie, because Neptune is not quiet, it is not peaceful, and it is not passive. Neptune is the most violent planet ever discovered and the most misunderstood. Its winds move faster than any storm we have ever measured, reaching speeds that should not be physically possible so far from the Sun. Its atmosphere releases more energy than it receives, breaking the basic rules we expect planets to follow. Its storms appear suddenly, grow to the size of Earth, then vanish without explanation, as if they are being switched on and off. Nothing about Neptune behaves the way a planet should. When Voyager 2 flew past Neptune in 1989, scientists expected a frozen, dying world. What they found instead shocked them. They saw supersonic winds. They saw extreme temperature gradients. They saw weather systems powered by an unknown internal engine. Voyager survived, barely, and then Neptune closed again. No spacecraft has returned since, not because we don't want to go back, but because Neptune is one of the most hostile environments we know how to imagine. If a spacecraft tried to descend into its atmosphere, it would be torn apart layer by layer. First by cold so extreme it freezes metals, then by winds strong enough to snap structures, then by pressures so intense they would crush electronics into nothing. There is no surface to land on, no stable layer to survive in, no safe altitude. Neptune does not welcome visitors. It destroys them. And the deeper scientists look, the more uncomfortable the questions become. Why does Neptune generate so much internal heat? Why are its storms so precisely structured? Why does its magnetic field behave so erratically, as if something inside is actively shaping it? Neptune doesn't feel like a dead world. It feels active, dynamic, engineered, almost like a system designed to tear apart anything that enters its domain. And that leads to a question most people never ask. What if Neptune isn't just a planet? What if it's a machine, not built by intelligence we recognize, but built by physics, pushed to its absolute limits? A planetary engine, a natural weapon, a destroyer of spacecraft. Because when you strip away the beauty, when you ignore the blue glow, Neptune doesn't behave like a planet at all. It behaves like something designed to survive and to destroy. And the closer we look, the less certain we become that Neptune is only nature at work. Neptune should not be this active. By every basic rule of planetary science, it should be quiet, cold, slow, a world gradually fading after billions of years in darkness. It orbits nearly 30 times farther from the Sun than Earth. At that distance, sunlight provides almost no usable energy. The planet receives less than 1/1000th of the solar energy Earth does. On paper, Neptune should be frozen and inert, a relic of early solar system history, slowly losing heat and motion. But when scientists began to truly study Neptune, that expectation collapsed. Because Neptune is not cooling down, it is still running. The first clue came from temperature measurements. Instruments detected that Neptune emits significantly more energy than it receives from the Sun. This excess heat is not small or negligible. It is substantial, measurable, and persistent. Neptune radiates roughly 2.5 times more energy than sunlight alone could explain. That fact alone forces an uncomfortable conclusion. Something inside Neptune is still generating power. This internal heat drives everything that makes Neptune dangerous. It fuels the planet's violent winds, sustains its massive storms, and keeps its atmosphere in constant motion. Without it, Neptune would resemble a dim, frozen sphere. With it, Neptune becomes the most extreme weather system in the solar system. The winds are the most obvious expression of this energy. Neptune's atmosphere moves at speeds that defy intuition. Some wind systems exceed 2,000 kilometers per hour, faster than the speed of sound on Earth. These are not localized storms or rare events. They are planet-wide flows, wrapping around Neptune's entire circumference. What makes this even more unsettling is where these winds come from. On Earth, wind is driven by sunlight. The sun heats different regions unevenly, creating pressure differences that move air. On Jupiter and Saturn, sunlight still plays a role, combined with internal heat. But on Neptune, sunlight is almost irrelevant. The energy driving these winds comes from below. Neptune's atmosphere is powered from the inside out. This creates a planetary engine that never rests. Heat rises from the deep interior, pushing upward through layers of gas and ice. As it moves outward, it accelerates massive atmospheric currents. The farther these currents travel, the faster they become, amplified by Neptune's rotation and the planet's unusual internal structure. The result is an atmosphere that behaves less like weather and more like machinery. Systems form, they accelerate, they maintain structure, and they persist far longer than expected. Then there are the storms. When Voyager 2 arrived, it photographed a massive storm system later named the Great Dark Spot. It was comparable in size to Earth, a swirling vortex of extreme winds embedded deep within Neptune's atmosphere. Scientists assumed it would behave like Jupiter's Great Red Spot, long-lived, slowly evolving, predictable. They were wrong. Within a few years, the Great Dark Spot vanished completely. Not weakened, not broken apart. Gone. Then, years later, similar dark storms appeared elsewhere on Neptune, at different latitudes, with similar structure, but no clear connection to the original system. These storms form, disappear, and reappear as if Neptune is reorganizing itself. This is not how passive planets behave. Neptune does not drift toward equilibrium. It resets. Its storms are not decaying remnants of ancient heat. They are active expressions of an internal process that is still ongoing. To understand why this matters, you have to consider what a spacecraft would face. A probe approaching Neptune does not encounter a thin, gentle atmosphere that gradually thickens. It enters a dynamic environment filled with violent wind shear. Different layers of the atmosphere move at different speeds and directions. Structures experience twisting forces they were never designed to withstand. Even before pressure becomes a problem, motion becomes lethal. As the probe descends, conditions worsen rapidly. Temperature drops initially, then rises as internal heat dominates. Pressure increases not gradually, but exponentially. Electronics designed to operate in vacuum or mild atmospheres begin to fail. Mechanical components seize. Structural elements bend and fracture. And there is no clear boundary marking where the atmosphere ends and Neptune truly begins. There is no surface. There is only depth. The deeper you go, the less recognizable matter becomes. Gases, compress into supercritical fluids. Hydrogen behaves in ways that cannot be reproduced in laboratories on Earth. Methane breaks apart, possibly forming solid carbon structures, what some scientists refer to as diamond rain. These are not poetic descriptions. They are attempts to describe matter under conditions we barely understand. Neptune is not just hostile because it is cold or distant. It is hostile because its internal physics push materials into regimes where human technology fails. The planet's magnetic field adds another layer of instability. Unlike Earth's magnetic field, which is centered and relatively stable, Neptune's is tilted and offset. It originates far from the planet's center and wobbles as Neptune rotates. This creates unpredictable regions of charged particles and radiation. A spacecraft passing through Neptune's environment would experience fluctuating radiation exposure, complicating shielding and system design. Instruments could degrade unevenly. Power systems could be disrupted without warning. This unpredictability is critical. Space exploration relies on planning. Neptune resists planning. Distance makes everything worse. Signals sent from Earth take more than 4 hours to reach Neptune. By the time a command arrives, conditions may have changed completely. Real-time control is impossible. Any spacecraft must make decisions on its own, reacting to an environment that even our best models cannot fully predict. That autonomy is a vulnerability. Neptune does not allow hesitation. It does not allow correction. Mistakes are not reversible. Voyager 2 survived because it never truly engaged Neptune. It skimmed past, gathered data, and escaped. Its success depended on distance and speed. Had it attempted to slow down or descend, the story would have ended differently. This is why Neptune has remained untouched for decades, not ignored, not forgotten, but avoided. It represents a boundary where curiosity collides with practicality, where exploration demands technology we do not yet have, where the environment is so extreme that even understanding it requires indirect observation and inference. And yet, Neptune continues to operate. Its winds continue to rage. Its storms continue to form and vanish. Its internal heat continues to rise. Neptune does not care whether it is studied. It does not respond to observation. It simply runs. In that sense, calling Neptune a machine is not metaphorical exaggeration. It is a recognition of how consistently and efficiently it converts internal energy into destructive output. There are no gears, no circuits, no intention, just physics operating at a scale that overwhelms anything fragile enough to enter. And this is only the beginning, because once you accept that Neptune is powered from within, that its atmosphere is driven by forces far beyond sunlight, and that its structure resists exploration by design of nature alone, you begin to realize something unsettling. Neptune is not an exception. It is a preview, and what it previews is a universe filled with worlds that look peaceful from afar, but operate under rules that make survival impossible. Neptune is not waiting to be explored. It is waiting to be understood. From a distance, Neptune is cold in a way that defies human intuition. On Earth, cold is something we experience as discomfort, a lack of heat, a temporary condition that can be escaped with shelter or energy. But on Neptune, cold is not an absence. It is an active force, one that shapes matter, motion, and failure. At Neptune's distance from the Sun, temperatures in the upper atmosphere drop to nearly -200 degrees Celsius. That number alone sounds extreme, but it does not capture the reality of what that cold does. At these temperatures, materials behave differently. Metals become brittle. Polymers lose flexibility. Lubricants freeze. Chemical reactions slow or stop entirely. For a spacecraft, this kind of cold is not survivable for long. Every probe ever built depends on controlled temperature. Electronics must remain within narrow operating ranges. Batteries lose efficiency as temperature drops. Power systems struggle to deliver consistent output. Even wiring insulation can crack under sustained exposure. Neptune does not allow warmth to linger. Any heat a spacecraft carries with it is slowly stripped away, radiated into space faster than it can be replenished. Heaters must run constantly just to prevent systems from freezing solid. That constant demand drains power, and power, this far from the sun, is scarce. Solar panels are almost useless at Neptune. Sunlight there is less than 1% as strong as it is near Earth. A solar-powered spacecraft would starve within days. This leaves only nuclear power, radioisotope generators that produce heat and electricity through decay. But even nuclear power has limits. The heat output of these systems is steady, not adjustable. As Neptune's environment pulls heat away faster than expected, systems designed to stay warm begin to fail at their edges. Cold seeps into connectors. Sensors lose calibration. Structural stresses build silently as different materials contract at different rates. And this is before the winds are even considered. Neptune's winds are not just fast. They are persistent. They flow continuously, wrapping around the planet in bands that never rest. Unlike Earth's atmosphere, where friction with the surface and uneven heating break storms apart, Neptune has no surface to slow anything down. Once motion begins, it continues. At certain altitudes, winds exceed 2,000 kilometers per hour. These flows are not gentle streams. They are violent shears, layers of atmosphere sliding past one another at radically different speeds. Anything moving through them is subjected to twisting forces from multiple directions at once. A spacecraft descending into Neptune would not experience a single direction of stress. It would be pulled, spun, bent, and shaken simultaneously. Antennas would snap, panels would tear away. Even compact, hardened probes would experience structural failure long before reaching deeper layers. Cold and wind work together. Extreme cold weakens materials. Extreme wind exploits that weakness. This combination is what makes Neptune especially destructive. Other planets may have high winds or low temperatures, but rarely both at this intensity, sustained over such a large scale. Neptune does not offer moments of calm. Its atmosphere is in constant motion, driven by energy rising from below. And that energy does not diminish with altitude. As a probe descends, conditions do not stabilize. They worsen. Pressure increases rapidly. Gases compress. What begins as atmosphere becomes fluid. What looks like empty space becomes something thick enough to push back. At a certain point, the idea of flying stops making sense. Motion becomes resistance. Descent becomes compression. Electronics fail not because of impact, but because pressure forces conductive pathways together. Insulation collapses, signals short. Systems that work perfectly in vacuum become useless in a dense, crushing environment. Neptune offers no clear boundary where a spacecraft can stop and operate safely. There is no equivalent to orbiting close above a solid surface. There is no platform to hover above. Every meter downward increases risk exponentially. And then there is the time problem. Because Neptune is so far away, every decision must be made hours in advance. By the time a signal reaches Earth, whatever caused it has already passed. By the time a response arrives, the spacecraft may no longer exist. Autonomy becomes mandatory, but autonomy requires predictability. Neptune provides none. Storms shift position. Wind speeds fluctuate. Temperature gradients change unexpectedly. Even the planet's magnetic field moves in ways that are difficult to forecast. This magnetic field traps charged particles, creating invisible radiation zones that drift and distort as Neptune rotates. Radiation damages electronics gradually, not all at once. It corrupts memory. It degrades sensors. It introduces errors that are difficult to detect until systems begin to behave strangely. In deep space, redundancy is survival, but redundancy adds mass. Mass increases launch cost. And at Neptune's distance, every kilogram matters. This is why missions to Neptune are rare. Not because we lack curiosity, but because every design choice becomes a compromise between survival and feasibility, between Neptune's demands and our limitations. Voyager 2 avoided most of these dangers by staying high and fast. It did not attempt to descend. It did not slow down. It did not challenge Neptune directly. It passed through the system like a whisper and left before Neptune could respond. That single flyby remains our closest encounter, and it may remain so for a long time. Because Neptune's cold is not passive. It is not simply the absence of heat. It is an active environment that drains energy, stiffens matter, and magnifies every other threat. Cold makes failure brittle. Wind makes failure violent. Distance makes failure irreversible. Together, they form a system that does not forgive mistakes. Neptune does not need extreme gravity to destroy spacecraft. It does not need solid ground or impacts or explosions. It dismantles visitors slowly, methodically, layer by layer. By the time anything reaches the depths where Neptune's true interior begins, it is no longer a probe. It is debris. And this reality forces a difficult conclusion. Neptune is not unexplored because we haven't tried hard enough. It is unexplored because it exists at the edge of what our technology can tolerate. Cold, wind, pressure, radiation, and distance combine into an environment where survival time is measured not in hours or days, but in moments. Neptune does not rush. It does not need to. It simply waits, operating exactly as it always has, confident that anything fragile enough to enter will eventually fail. And in that sense, Neptune's cold is not just temperature. It is a filter, a test, a boundary beyond which exploration becomes destruction. Neptune's winds are not storms in the way we understand storms on Earth. They are not temporary. They do not build and collapse. They do not wait for sunlight or seasonal change. They exist continuously, wrapping around the planet in vast, organized flows that never stop moving. On Earth, wind is a surface phenomenon. Air moves because sunlight heats the ground unevenly. Warm air rises, cool air sinks, and the atmosphere circulates to compensate. Friction with land and ocean slows everything down. Mountains disrupt flow. Storms exhaust themselves. Neptune has none of these limits. There is no solid surface to absorb energy, no terrain to break momentum, no oceans to damp motion. Once Neptune's atmosphere begins to move, nothing slows it down. The fastest winds ever measured in the solar system are found here. Some exceed 2,000 kilometers per hour. These are not localized bursts or rare extremes. They are sustained, global currents that sweep across the planet's atmosphere year after year. What makes this even more unsettling is that these winds should not exist at all. Neptune receives almost no energy from the Sun. At its distance, sunlight is too weak to drive powerful atmospheric circulation, and yet Neptune's winds are stronger than those on Jupiter, Saturn, or Uranus, planets that receive significantly more solar energy. This forces an unavoidable conclusion. Neptune's winds are not powered from above. They are driven from below. Deep inside Neptune, heat is rising. This heat moves upward through layers of gas and ice, carrying energy into the atmosphere. As it reaches higher altitudes, it accelerates massive wind systems, feeding them continuously. The planet rotates once every 16 hours. That rotation twists rising heat into organized jets that encircle the planet. These jets interact, collide, and shear against each other, creating an atmosphere in constant tension. Different layers move at different speeds. Some flow eastward, others move westward. Vertical motion mixes with horizontal motion, creating a three-dimensional storm system that never stabilizes. For a spacecraft, this environment is catastrophic. Imagine descending into an atmosphere where the air above you moves in one direction, the air below you moves in another, and the air beside you moves faster than either. Structural stress builds instantly. Forces pull in opposing directions. Components designed to withstand vibration experience twisting instead. Even if a probe were designed to survive extreme wind from a single direction, Neptune offers no such simplicity. Wind shear is the real danger. At certain altitudes, adjacent atmospheric layers differ in speed by hundreds of kilometers per hour. A descending object passes through these layers in seconds, experiencing rapid changes in force. This produces oscillations that grow uncontrollably. Antennas snap, panels tear away, housings fracture along seams. And because Neptune's winds are sustained, not episodic, there is no window of calm. There is no moment to recover or correct orientation. The atmosphere does not pause. The deeper a probe descends, the worse the shear becomes. Density increases, turning wind into something with real mass and momentum. What begins as gas becomes fluid-like, pushing back with increasing resistance. At a certain point, wind stops being movement through air. It becomes impact. This is why Neptune storms are so destructive even to themselves. Large storm systems form as coherent structures, maintaining shape for months or years. But eventually, the same winds that sustain them tear them apart. Storms collapse not because they weaken, but because internal stresses exceed what even Neptune's atmosphere can hold together. Then later, new storms appear. Not randomly, not slowly, but suddenly, as if the system resets and tries again. This behavior suggests that Neptune's atmosphere is constantly balancing competing forces: internal heat, rotation, magnetic effects, and pressure gradients. When equilibrium is lost, the system reorganizes violently. For spacecraft designers, this is a nightmare scenario. Every mission relies on assumptions about stability. Engineers predict environments based on models, margins, and probabilities. But Neptune's winds defy long-term prediction. They are shaped by internal processes we cannot directly observe. We infer Neptune's interior from gravitational measurements, magnetic data, and atmospheric motion. These indirect clues suggest a layered structure unlike any other planet. Deep beneath the visible clouds may exist exotic states of matter, supercritical fluids where distinctions between gas and liquid disappear. In these regions, energy moves differently. Heat does not dissipate smoothly. It surges upward in pulses, feeding the atmosphere unpredictably. This explains why Neptune's wind speeds vary dramatically by latitude. Some regions race forward at incredible velocity, while others lag behind or even reverse direction. The planet's atmosphere is not a single system. It is a stack of interacting systems, each driven by forces below, and every one of them is hostile to intrusion. A spacecraft entering Neptune's atmosphere would not simply fall downward. It would be caught, spun, accelerated sideways, and slammed into denser layers at oblique angles. Control systems would struggle to maintain orientation. Thrusters would be useless against sustained winds of this magnitude. At these speeds, even small structural irregularities become critical failure points. Vibration builds, resonance develops. What begins as minor oscillation becomes catastrophic instability. This is not theoretical. We see similar effects on Earth at much smaller scales. Aircraft avoid thunderstorms, not because of rain, but because of wind shear. Sudden changes in airspeed and direction can overwhelm control surfaces instantly. Now imagine that effect multiplied thousands of times and sustained indefinitely. Neptune's winds are not weather. They are a planetary scale mechanism. They do not move air to restore balance. They move air because balance does not exist. The planet's internal heat never equalizes. Its rotation never slows enough to damp motion. Its lack of a solid surface removes friction entirely. What remains is an atmosphere locked in perpetual acceleration. This is why Neptune cannot be approached casually. Any attempt to study it directly must contend with forces that act continuously, not episodically. There is no safe altitude where winds become manageable. There is no layer where motion slows to tolerable levels. Even hovering is impossible. Even slowing down is dangerous. And unlike planets closer to the Sun, Neptune does not advertise its danger clearly. From a distance, its blue appearance suggests calm. Its storms lack the obvious violence of Jupiter's lightning-filled clouds. Its winds are invisible unless measured. This makes Neptune deceptive. It looks peaceful because its violence is organized, smooth, efficient, relentless. And that efficiency is what gives rise to the idea of Neptune as a machine, not because it was built, but because it operates. Its winds convert internal energy into motion with astonishing effectiveness. They distribute force globally. They maintain structure. They destroy intruders without direct impact. Neptune does not need explosions or collisions. It dismantles through motion. And because that motion is sustained by processes deep within the planet, it does not weaken over time. Neptune is not calming down. It is not running out of fuel. It is still young in behavior, even if it is ancient in age. This realization changes how we think about the outer solar system. Neptune is not a distant curiosity. It is a warning that planets can exist in states far more extreme than our intuition allows, that environments can be hostile, not because they are chaotic, but because they are stable in ways that exclude us. The winds of Neptune are not an obstacle to overcome. They are a boundary. one that reminds us that exploration is not only about reaching places. It is about recognizing when a place cannot be entered, because the physics that sustain it are fundamentally incompatible with our presence. And Neptune's winds make that incompatibility unmistakably clear. Neptune does not become more forgiving as you go deeper. It becomes less recognizable. Above its cloud tops, Neptune still looks like a planet. Blue hues, moving bands, storms that can be photographed and tracked. But as you descend, the idea of a familiar atmosphere dissolves. What looks like gas begins to behave like something else entirely. There is no surface waiting below. There is only increasing pressure. On Earth, pressure increases slowly with depth. A few meters underwater add noticeable force. A few kilometers become dangerous. But Neptune compresses its atmosphere far more aggressively. Every layer below the clouds adds weight at a rate that accelerates rapidly. What begins as air becomes something thick enough to push back, to resist motion, to crush. A descending spacecraft would feel this change almost immediately. At first, instruments would register rising pressure as a manageable variable. Systems are designed for that. But Neptune does not increase pressure in a linear way. The deeper you go, the faster conditions escalate. Structures that were safe moments earlier suddenly find themselves operating far beyond their limits. This is where the word atmosphere stops being useful. Neptune's lower layers are not simply denser gas. They are regimes where matter exists in states we rarely encounter. Hydrogen and helium compress into supercritical fluids. Methane molecules are torn apart by pressure and temperature. Carbon atoms may bond into solid structures and fall like rain. These are not poetic descriptions. They are predictions based on physics pushed into extremes. As pressure increases, the distinction between solid, liquid, and gas blurs. Materials behave unpredictably. Mechanical systems lose meaning because there is no clear medium to move through. Motion becomes resistance. Descent becomes compression. A probe entering these depths would experience forces acting uniformly from every direction. Unlike impact or collision, this pressure does not strike suddenly. It builds relentlessly, squeezing structures until they deform, then fail. Electronics are especially vulnerable. As pressure rises, insulation collapses. Conductive pathways shift. Circuits short not because they are damaged, but because they are physically forced together. Sensors saturate. Calibration becomes meaningless. Signals distort until data is no longer interpretable. At a certain depth, even the concept of failure loses clarity. Systems do not break cleanly. They cease to function because the environment no longer allows their principles to apply. The materials used in spacecraft are chosen carefully. Aluminum alloys, titanium, composites, each selected for strength, weight, and reliability. But these materials are designed for vacuum, radiation, and mild atmospheric entry. They are not designed for sustained exposure to crushing pressure combined with violent motion. Neptune offers no chance to adapt. There is no intermediate layer where conditions stabilize. Every meter downward is worse than the last. Pressure doubles, then triples, then rises beyond anything tested on Earth. Even our strongest pressure vessels, those used to explore the deepest oceans, would fail quickly. And those vessels are designed to resist static pressure, not pressure combined with wind shear, temperature gradients, and chemical aggression. Neptune does not apply stress from one direction. It applies it from all directions at once, and pressure is only part of the story. As depth increases, temperature rises. Despite Neptune's reputation as a frozen world, its interior is hot. Heat generated during the planet's formation remains trapped beneath layers of ice and fluid. That heat moves upwards slowly, fueling storms and winds. But deeper down, it becomes intense. Temperature increases compound pressure. Materials expand while being compressed. Structural stresses multiply. Bonds weaken. Chemical reactions accelerate in unexpected ways. This combination, high pressure and high temperature, creates environments that are hostile not just to life, but to structure itself. Anything that descends far enough becomes unstable. This is why Neptune cannot be landed on in any meaningful sense. There is no moment when descent ends and exploration begins. There is no transition from falling to resting. There is only continuous immersion into an environment that grows more extreme with depth. The deeper you go, the less control you have. Thrusters lose effectiveness as surrounding material thickens. Control surfaces become irrelevant. Orientation systems fail as sensors are overwhelmed. Communication becomes impossible long before destruction occurs. And even if a probe were somehow reinforced enough to survive greater depths, it would face another problem. We do not know where Neptune truly ends. Unlike rocky planets, Neptune has no clear boundary between atmosphere and interior. Its layers transition gradually. Gas becomes fluid. Fluid becomes something denser still. Eventually, the planet's interior blends into a region of exotic matter under pressures millions of times greater than Earth's atmosphere. This uncertainty matters. Exploration depends on knowing where you are going. On Neptune, there is no clear destination. There is no depth at which conditions suddenly become stable or manageable. Every layer introduces new unknowns, and unknowns are dangerous. This is where Neptune's reputation as a destroyer becomes unavoidable. It does not rely on sudden catastrophe. There is no explosion, no dramatic impact. Neptune dismantles slowly, understanding nothing of haste. It applies pressure steadily until structure yields. It raises temperature until materials soften. It surrounds intruders with forces they cannot resist. This is a system designed by physics to erase complexity. Complex systems require balance. They require controlled conditions. Neptune removes control. And once control is gone, collapse follows naturally. This has profound implications for exploration. It means that Neptune is not simply hard to reach. It is hard to survive even conceptually. Designing a probe capable of descending deeply would require materials and technologies that can tolerate conditions beyond current limits. It would require sensors that function without calibration, systems that operate without stable reference frames, and structures that do not rely on conventional mechanical principles. In other words, it would require a fundamentally different approach to exploration. This is why most proposed Neptune missions focus on orbiting or flybys rather than descent. Observing from a distance remains the only viable option, and even orbiting Neptune presents challenges due to radiation, gravity, and atmospheric drag at lower altitudes. Neptune enforces separation. It allows observation. It resists interaction. And this resistance is not accidental. It emerges from the planet's structure itself. Pressure, temperature, and depth combine into a layered defense. Not intentional, not designed, but effective. Neptune is not hostile because it wants to be. It is hostile because it cannot be anything else. Its internal heat demands release. Its mass demands compression. Its lack of a solid surface demands motion. These demands produce an environment that excludes fragile systems. This realization changes the tone of exploration. Neptune is not a challenge to overcome through bravery or ingenuity alone. It is a reminder that some environments operate beyond our tolerance, not because we are weak, but because physics allows no compromise. The deeper you go, the more Neptune becomes itself, and the less anything else can remain intact. Pressure does not negotiate, temperature does not pause, depth does not forgive. Neptune simply continues, layer by layer, converting distance into destruction. And in doing so, it teaches a quiet lesson. Not all worlds are meant to be touched. Some exist only to be observed from afar, because approaching them means surrendering the very systems that make exploration possible. Neptune is one of those worlds, and pressure is its most patient weapon. Neptune's violence is not only physical, it is also invisible. Even if a spacecraft could somehow survive the cold, the winds, and the crushing pressure, it would still face an environment that attacks it in ways that are harder to see and even harder to predict. Neptune's magnetic field is unlike anything humans are accustomed to. On Earth, the magnetic field is relatively simple. It is centered close to the planet's core, aligned roughly with the axis of rotation, and stable enough that navigation systems and radiation models can rely on it. It creates a protective bubble that shields the planet from much of the sun's charged particles. Neptune's field does none of this cleanly. It is tilted by nearly 50 degrees relative to the planet's rotation. It is offset from the planet's center by thousands of kilometers, and it changes orientation as Neptune spins. This means that the magnetic environment around Neptune is constantly shifting. For a spacecraft, this creates a serious problem. Magnetic fields trap charged particles. They accelerate them. They turn regions of space into invisible radiation zones, where high-energy particles move at extreme speeds. On Neptune, these regions are not neatly arranged or predictable. They drift, stretch, and collapse as the planet rotates. A spacecraft passing through Neptune's magnetosphere would experience radiation exposure that varies rapidly over time and position. Instruments could be damaged unevenly. Electronics might degrade gradually, producing errors that are difficult to diagnose until it is too late. Radiation does not announce itself. It corrupts memory. It flips bits. It weakens components silently. Systems may continue to function while becoming unreliable, producing data that looks valid but is subtly wrong. For exploration, this is one of the most dangerous failure modes possible, and Neptune's magnetic field is only part of the problem. The planet is surrounded by charged particle populations that interact with its atmosphere and rings. These particles spiral along magnetic field lines, colliding with atmospheric gases and releasing energy. This interaction contributes to Neptune's auroras, faint, ghostly glows near the poles, but it also injects energy directly into the upper atmosphere. This energy adds to the instability already present. Instead of a calm transition from space to atmosphere, a spacecraft would encounter layers of charged particles, radiation, and ionized gas before even reaching the clouds. Communication signals could be distorted or absorbed. Sensors could be overwhelmed by noise. Navigation systems could lose accuracy. This matters because at Neptune's distance, precision is everything. With communication delays of more than 4 hours, a spacecraft cannot rely on instructions from Earth. It must interpret its environment and react on its own. That autonomy depends on clean data and predictable behavior. Neptune offers neither. Magnetic disturbances can interfere with star trackers and gyroscopes. Radiation can disrupt processors and memory. Atmospheric interactions can create unexpected forces on the spacecraft's structure. Even if no single factor causes immediate failure, the combination steadily erodes reliability. This is how Neptune destroys machines. Not with sudden catastrophe, but through accumulation. A slight sensor drift here, a corrupted data packet there, a weakened component that fails at the worst possible moment. By the time a spacecraft shows obvious signs of distress, the damage has already been done. Voyager 2 experienced this environment briefly. During its flyby, it recorded Neptune's magnetic field and detected its unusual structure. But Voyager passed through quickly. It did not remain long enough to experience sustained exposure. Even so, the data it returned raised alarms. Neptune's magnetic behavior suggested that any long-term mission would face an environment far more complex than anticipated. Designing shielding for such variability is difficult. Shield too little, and systems degrade. Shield too much, and mass increases beyond feasible limits. Every kilogram added for protection must be launched from Earth, accelerated across billions of kilometers, and managed carefully throughout the mission. This is the constant trade-off of deep space exploration, protection versus practicality. Neptune pushes that trade-off to the breaking point. The farther a spacecraft travels from Earth, the more it must rely on itself. Repairs are impossible. Upgrades are unthinkable. Redundancy helps, but redundancy has limits. When the environment itself undermines every system simultaneously, redundancy only delays failure. This is why Neptune is not just physically destructive, but operationally destructive. It attacks the assumptions that make exploration possible. We assume sensors will remain accurate. We assume computers will process reliably. We assume communication will function intermittently, but sufficiently. Neptune challenges all of these assumptions at once. Its radiation environment does not simply damage components. It introduces uncertainty, and uncertainty is fatal to complex systems. This is also why humans could never see Neptune directly. A human body is far more vulnerable to radiation than any spacecraft. Even short exposure to Neptune's magnetospheric environment would be dangerous. Prolonged exposure would be lethal. Protective shielding thick enough to block this radiation would be impractical for human missions. And even if shielding were possible, the isolation would remain. Neptune is so distant that rescue is not an option. Medical emergencies could not be treated. Psychological strain would compound over years of travel. Any failure would be final. But the most unsettling aspect of Neptune's invisible violence is that it is largely self-sustaining. The planet's internal heat drives atmospheric motion. Atmospheric motion interacts with the magnetic field. The magnetic field accelerates particles. Those particles feed energy back into the atmosphere. It is a loop, not perfectly closed, not fully understood, but persistent. This feedback may help explain why Neptune remains so active despite its distance from the Sun. Energy circulates within the system, redistributed rather than dissipated. The planet does not need external input to remain violent. It generates its own hostility. And because this hostility is distributed across multiple domains, thermal, mechanical, magnetic, radiative, it cannot be countered with a single solution. You cannot shield against everything. You cannot predict everything. You cannot adapt quickly enough. Neptune overwhelms by complexity. This is why describing Neptune as a machine resonates. Machines are systems where components interact continuously, producing consistent outcomes. Neptune's components, heat, motion, magnetism, radiation, interact in ways that reliably destroy fragile systems. Not occasionally, not randomly, but inevitably. Anything entering Neptune's environment becomes part of that system, and once integrated, it is subject to forces it cannot escape. Neptune does not hunt, it does not defend. It simply continues operating exactly as it always has. And in doing so, it exposes a limit we rarely confront. There are places in the universe where intelligence, engineering, and ambition are irrelevant, where the environment itself is the dominant force, shaping outcomes regardless of intent. Neptune is one of those places. Its invisible forces are as destructive as its visible storms, and together they form an environment that is not just dangerous to explore, but fundamentally incompatible with the tools we use to explore. This is not a failure of imagination. It is a reminder of scale. Neptune is vast. Its processes are ancient. Its systems are self-sustaining. And anything that enters, no matter how advanced, is temporary. The machine does not notice. It does not slow down. It does not change. It simply continues, layer by layer, field by field, quietly dismantling whatever crosses into its reach. Distance is what makes Neptune truly unreachable. Not just physical distance, but temporal distance. The kind that stretches decisions, consequences, and mistakes across hours, days, and years. Neptune orbits the Sun nearly 4.5 billion kilometers from Earth. At that range, space stops behaving like a place you can interact with. It becomes something you must anticipate long before you arrive. A radio signal sent from Earth to Neptune takes more than 4 hours to arrive. A reply takes another 4 hours to return. By the time a problem is noticed, acknowledged, and responded to, nearly half a day has passed. In deep space, that delay is not inconvenient. It is fatal. Every spacecraft we send beyond the inner solar system depends on autonomy. But autonomy has limits. It relies on accurate sensors, reliable models, and predictable environments. Neptune undermines all three. If a spacecraft approaching Neptune encounters unexpected wind shear, radiation spikes, or thermal stress, there is no way for Earth to intervene in time. The probe must decide instantly using data that may already be compromised. At Neptune, every decision happens in isolation. There is no live control, no second chances, no human judgment. This turns exploration into a gamble. Space missions are designed with contingency plans, but contingencies depend on knowing what can go wrong. Neptune introduces unknowns that cannot be fully anticipated. Its storms evolve unpredictably. Its magnetic field shifts. Its radiation environment fluctuates. A spacecraft must respond to conditions that may never have been encountered before. And when it responds incorrectly, there is no correction. Distance also magnifies fragility. The farther a spacecraft travels, the longer it must survive without maintenance. Components age, radiation damage accumulates. Mechanical wear progresses slowly but steadily. Even in empty space, systems degrade. By the time a probe reaches Neptune, it has already spent more than a decade in transit. Many of its systems are operating well beyond their original design lifetimes. Redundancies may have been used. Backup systems may already be degraded. Neptune is not the beginning of the mission. It is the end of a long process of attrition. This is why Voyager 2's survival is often misunderstood. Voyager did not arrive at Neptune fresh and intact. It arrived after 12 years of exposure to radiation, micrometeoroids, thermal cycling, and gradual wear. By the time it reached Neptune, Voyager was already vulnerable, and yet it had to face one of the most extreme environments in the solar system. It survived only because it passed quickly. It did not slow down. It did not orbit. It did not descend. It collected data and escaped. Any mission attempting more would face a different reality. Orbiting Neptune requires shedding enormous amounts of speed. That means prolonged exposure to its gravity and magnetosphere. It means extended time within regions of intense radiation. It means repeated passes through unstable atmospheric drag zones. Every orbit increases risk. Every maneuver introduces failure points. Distance ensures that once something goes wrong, it stays wrong. Even software updates become dangerous. Uploading new instructions across billions of kilometers introduces the risk of corruption. A single error in a command sequence could render a spacecraft useless. At Neptune, you cannot reboot and try again. The machine either continues to function or it doesn't. Distance also isolates humans psychologically, even when they are not physically present. Mission planners must think years ahead. Decisions made today may not have consequences until a decade later. Errors are discovered long after they can be fixed. This temporal separation creates a kind of blindness. You design for Neptune without ever seeing Neptune directly. You rely on simulations, models, and assumptions. You commit to trajectories and hardware long before reality can contradict you, and Neptune waits. By the time a spacecraft arrives, the design is frozen. The hardware is old. The assumptions are tested not gradually, but all at once. This is why Neptune feels less like a destination and more like a verdict. You do not negotiate with it. You do not adjust once you arrive. You discover whether your decisions were correct or catastrophic. Distance also limits what can be learned. Because communication is slow, data must be compressed, prioritized, and rationed. Instruments cannot send everything. Scientists must choose what matters most before the spacecraft even arrives. That choice carries risk. Focus too narrowly, and you miss unexpected phenomena. Spread attention too widely, and critical data is lost. Neptune's complexity demands flexibility, but distance enforces rigidity. This tension is what makes Neptune such a difficult target. It is not just far away, it is far away in time. Years pass between launch and arrival. Technologies advance, knowledge improves, but the spacecraft remains locked in the past, carrying outdated hardware and software into an environment that may be more complex than anticipated. Neptune exposes the cost of delay. It forces exploration to commit to decisions long before understanding is complete. And once committed, there is no turning back. For humans, this problem becomes existential. A human mission to Neptune would take decades, Life support systems would have to function flawlessly for years. Psychological strain would accumulate without relief. Medical emergencies would be untreatable. Supplies could not be replenished. And even if humans somehow arrived intact, Neptune would still be waiting. Cold, violent, unforgiving. Distance means that failure is not dramatic. It is quiet. A system stops responding. A signal goes silent. A mission ends without explanation. Earth waits hours, then days, then years, hoping for a reply that will never come. This is why Neptune is not just a technological challenge. It is a philosophical one. It forces us to confront the limits of exploration itself, to ask whether every place must be visited physically to be understood, to recognize that some environments are better studied from afar through indirect observation and patience. Neptune teaches humility. It reminds us that distance is not just space between objects. It is time between cause and effect, between decision and consequence. And at Neptune, that distance is vast. The planet does not rush. It does not react. It does not adapt to us. It simply continues operating, indifferent to the tools we send toward it. And the farther away we are, the more absolute that indifference becomes. Distance turns Neptune into something more than a planet. It turns it into a boundary, a place where exploration slows, where control fades, and where the universe reminds us that not all frontiers can be crossed. Not because we lack courage, but because the cost of crossing them may exceed what we can endure. Neptune does not reject us violently. It rejects us quietly, through distance. Neptune does not overwhelm spacecraft immediately. It wears them down. Failure at Neptune is rarely sudden. It is gradual, cumulative, and almost impossible to reverse. Systems do not explode or shatter all at once. They degrade, they drift. They begin to behave strangely long before they stop working entirely. This is what makes Neptune especially dangerous. In most extreme environments, danger announces itself. A spike in temperature, a sudden impact, a violent collision. Neptune's destruction is quieter. It happens through small, persistent stresses that add up over time. Every spacecraft is built with margins, extra strength, backup systems, tolerances meant to absorb unexpected strain. Those margins are slowly consumed as a mission progresses. By the time a probe reaches Neptune, many of those margins are already gone. Years of travel through interplanetary space expose spacecraft to radiation from the sun and cosmic sources. Tiny particles strike exposed surfaces. Thermal cycles stress materials as the craft moves between sunlight and shadow. Electronics age. Mechanical parts wear. None of this is catastrophic by itself, but it weakens the system. When the spacecraft finally encounters Neptune's environment, it does so in a compromised state. Components that once functioned flawlessly are now less resilient. Redundant systems may have already been used. Protective coatings may be degraded. Neptune exploits that weakness. Radiation near Neptune does not usually destroy systems instantly. Instead, it causes gradual damage. High-energy particles pass through electronic components, displacing atoms, creating defects, and altering electrical behavior. Memory bits flip, sensors drift out of calibration, processors begin to misinterpret signals. These errors are subtle at first. Data still arrives, telemetry still looks reasonable, but something is off. Measurements no longer align perfectly. Control systems compensate for conditions that no longer exist. The spacecraft begins to lie to itself. This is one of the most dangerous failure modes in engineering. Systems appear functional while slowly diverging from reality. Commands based on faulty data produce incorrect responses. Those responses generate new data that reinforces the error. Feedback loops form. At Neptune, these loops are amplified by the environment. Winds introduce unpredictable forces. Magnetic fields distort measurements. Radiation corrupts memory. Each factor feeds the others. A small sensor error leads to incorrect orientation. Incorrect orientation exposes the spacecraft to greater stress. Greater stress accelerates degradation. The spiral tightens. Autonomous systems are designed to handle known problems. They are not designed to recognize when their own perception is flawed. At Neptune's distance, there is no human oversight to notice subtle inconsistencies and intervene. Earth receives delayed data. By the time engineers see a problem, it may have already cascaded beyond recovery. This is why Neptune is not just physically destructive, but informationally destructive. It undermines the data upon which decisions are made. Communication itself becomes unreliable. Charged particles interfere with radio signals. The planet's ionosphere can distort transmissions. Noise increases. Error correction struggles. Data packets arrive incomplete or corrupted. Some are lost entirely. Mission planners must decide whether missing data indicates transmission failure or system failure. That ambiguity delays response. And delay at Neptune is fatal. The spacecraft is always moving forward in time. Damage accumulates whether anyone is watching or not. Even if systems remain operational, the sheer duration of exposure becomes a problem. Neptune does not offer a quick encounter unless the mission is deliberately designed to flee. Any attempt to orbit or linger extends exposure to all of these destructive processes. Orbit insertion itself is hazardous. Slowing down near Neptune requires precise maneuvers. Errors of timing or thrust can send a spacecraft too deep into atmospheric drag or too close to radiation belts. Each maneuver burns fuel. Fuel is finite. Once spent, it cannot be replaced. As fuel reserves drop, control options narrow. The spacecraft becomes less able to respond to unexpected conditions. It grows more passive, more vulnerable. Neptune does not need to act aggressively. It simply waits while the spacecraft exhausts itself. This slow attrition is why Neptune has resisted repeated visits. Each mission would require extraordinary reliability over decades, followed by survival in one of the harshest environments known. And even then, success would be fragile. One unexpected storm, one magnetic fluctuation, one corrupted memory sector. The mission ends not with impact, but with silence. This pattern forces a sobering realization. Exploration is not defeated by dramatic failure. It is defeated by time. Neptune is far enough away that time becomes an adversary. Every system ages before it arrives. Every design decision is tested years after it is made. Every error is discovered too late to fix. The planet does not rush this process. It allows degradation to proceed naturally. This is why Neptune feels less like a hostile enemy and more like an environment that simply does not accommodate complexity. It does not destroy machines out of violence, but out of indifference. Complex systems require stability. Neptune provides none. Its environment changes subtly but continuously. Magnetic fields shift, Atmospheric flows evolve. Radiation levels fluctuate. There is no steady baseline against which systems can anchor themselves. Without a baseline, calibration becomes guesswork. Without calibration, control becomes unstable. Eventually, the spacecraft is no longer operating within the parameters it was designed for. It is operating within Neptune's parameters. And Neptune's parameters do not include survival. This reality also reshapes how we think about future missions. Sending a probe to Neptune is not just about building something strong enough. It is about building something that can remain coherent, physically, electronically, and informationally, across decades of exposure to hostile conditions. That is a far more difficult problem than raw strength. Strength resists force, coherence resists entropy. Neptune accelerates entropy. Every interaction pushes systems toward disorder. Every fluctuation increases uncertainty. Over time, the accumulation of small failures becomes inevitable. This is why Neptune feels like a machine. Not because it was engineered, but because it consistently produces the same outcome. Anything complex that enters its domain begins to simplify. Structures weaken, functions degrade, information is lost. Eventually, what remains is no longer a functioning system, just fragments. Neptune does not need to strike. It allows physics to do the work. And in that sense, Neptune represents a boundary not only of distance, but of complexity itself, a place where the universe reminds us that intricate systems are temporary and that some environments erase them patiently without drama. Neptune does not shout. It does not threaten. It waits. And over time, it dismantles everything fragile enough to try. Neptune is not alone. Its destructive nature becomes even more apparent when you look at the space around it. A system shaped by gravity, motion, and isolation in ways that amplify every danger rather than soften it. Neptune's moons do not orbit gently. They move through a gravitational environment that is unstable, tilted, and constantly changing. The planet's mass dominates everything nearby, bending trajectories and altering paths in ways that are difficult to predict precisely. At this distance from the Sun, gravity is no longer moderated by frequent encounters with other large bodies. Neptune's influence is absolute within its domain. Anything that enters its system must obey its rules completely. This makes navigation extremely difficult. A spacecraft approaching Neptune must account not only for the planet's gravity, but for the complex interactions between Neptune, its moons, and the Sun's distant pull. Small errors in trajectory can grow over time, pulling a probe into dangerous regions or forcing it to expend precious fuel to correct its course. Fuel is life. Every correction costs mass. Every maneuver reduces options. And once fuel is gone, control ends. Neptune's gravity does not forgive mistakes. Its pull accelerates objects rapidly as they approach. A miscalculated trajectory can turn a controlled flyby into an uncontrolled descent. At Neptune's scale, there is little margin between close enough to study and too close to survive. Orbiting Neptune is especially dangerous because of this. Unlike planets closer to the Sun, Neptune's weak solar influence means that orbits are shaped primarily by the planet itself. Minor disturbances persist longer. Errors compound rather than dampen. Once a spacecraft is captured by Neptune's gravity, escaping requires energy. If systems are degraded or fuel is limited, escape may be impossible. Neptune does not need an atmosphere to trap you. Gravity alone can do it. Then there are the moons. Triton, Neptune's largest moon, is unlike any other large moon in the solar system. It orbits Neptune backward, a retrograde orbit that suggests it was captured rather than formed in place. This capture would have been violent, reshaping Neptune's system and destabilizing any previous moons. Even today, Triton's presence distorts Neptune's gravitational environment. Its orbit interacts with Neptune's gravity in ways that create subtle but persistent perturbations. For spacecraft, this means unpredictability. Triton's gravity can alter trajectories during close passes. Its influence must be modeled carefully, but those models depend on assumptions that may not hold under real conditions. A slight miscalculation could place a spacecraft on a collision course or force it into an unintended orbit. Neptune's ring system adds another layer of risk. Though faint, Neptune's rings are irregular and clumpy. Unlike Saturn's broad, stable rings, Neptune's rings contain dense arcs that can concentrate material into localized regions. These regions may contain debris large enough to damage spacecraft at high relative speeds. At Neptune's orbital velocities, even small particles carry immense kinetic energy. A collision with debris the size of a pebble could be catastrophic. Because Neptune is so distant, tracking this debris accurately is difficult. Observations from Earth provide limited resolution. By the time a spacecraft arrives, conditions may have changed. Navigation near Neptune is therefore an exercise in managing uncertainty. You must assume hazards you cannot see. You must plan for disturbances you cannot measure directly. You must commit to paths you cannot adjust easily. This is the reality of operating at the edge of the solar system. Neptune's system magnifies isolation. There are no nearby planets to provide gravity assists for correction. There are no quick escape routes. Once inside Neptune's domain, you are committed, and commitment is dangerous when the environment is hostile. This is why Neptune's moons, rings, and gravity field together form a kind of extended barrier, not a wall, but a region where risk accumulates rapidly. Even if a spacecraft avoids the atmosphere entirely, it is still vulnerable. Radiation exposure continues. Gravitational stress persists. Fuel drains steadily. Time becomes the enemy again. Every orbit increases exposure. Every pass compounds damage. Neptune does not force destruction quickly. It allows it to build. This environment also limits scientific opportunity. High-resolution mapping requires close passes. Close passes increase risk. Staying farther away reduces data quality. Every mission must choose between safety and knowledge. Neptune forces compromise. It does not allow maximal exploration. It demands restraint. This is one reason why Neptune has been studied so little compared to Jupiter or Saturn. Those planets are closer, better understood, and offer more opportunities for correction. Neptune offers none of these advantages. It is distant, it is isolated, it is unforgiving, and yet it remains compelling. Because Neptune represents something larger than itself, it is a reminder that planetary systems are not just collections of worlds. They are dynamic environments shaped by gravity, motion, and time. Some systems are navigable, others are not. Neptune's system belongs to the latter category. It is not designed to host visitors. Its moons orbit in ways that reflect ancient violence. Its rings hint at instability. Its gravity dominates absolutely, Everything within Neptune's reach is shaped by it, and anything that enters must either escape quickly or be changed irreversibly. This reality reframes exploration. Neptune is not simply a distant planet waiting for better technology. It is a system that challenges the very assumptions of exploration, that proximity equals understanding, that persistence guarantees success. At Neptune, proximity increases danger, persistence increases risk. Understanding must come from patience and distance, from observation rather than intrusion. Neptune does not reward boldness, it rewards caution. Its system does not open itself easily. It reveals itself only in fragments, through careful measurement and indirect inference. And even then, it retains its secrets. This is why Neptune feels less like a destination and more like a boundary, a place where gravity, isolation, and complexity converge to say, this far and no farther. Not because the universe forbids exploration, but because it reminds us that not every frontier can be crossed safely. Neptune stands as one of those reminders, a distant system where every path is narrow, every decision costly, and every mistake permanent. And beyond it, there is only deeper darkness, which makes Neptune not just the edge of the solar system, but the edge of what we can reasonably touch. Neptune's danger is not limited to machines. If humans ever tried to go there, the planet would not challenge our technology first. It would challenge our biology. The human body evolved under very specific conditions: stable gravity, a narrow temperature range, a protective magnetic field, and constant access to sunlight. Neptune removes all of these at once. Long before a human ever reached Neptune, the journey itself would begin to break them down. A crewed mission would take decades, not years, decades. During that time, the human body would live in microgravity, slowly losing bone density and muscle mass despite exercise. The cardiovascular system would weaken. Vision could deteriorate as fluids shift inside the skull. The immune system would change in ways we still do not fully understand. These effects are already observed on missions lasting months. At Neptune, they would accumulate over a lifetime. Radiation exposure would add another layer of damage. Outside Earth's magnetic shield, cosmic radiation passes through the body continuously. Over years, this increases cancer risk, damages DNA, and accelerates aging. Shielding helps, but shielding adds mass, and mass increases mission complexity. Even with protection, radiation exposure on a decades-long mission would be extreme. By the time humans reached Neptune, they would already be compromised. But arrival would not bring relief. Neptune offers no place to land, no orbit that feels safe, no stable environment where humans could rest or recover. The planet's gravity, radiation environment, and atmospheric behavior make proximity itself dangerous. Any crewed spacecraft would need to remain at a significant distance, relying on remote instruments to study the planet indirectly. That distance would isolate the crew even further. Communication delays would stretch conversations into hours-long exchanges. Real-time contact with Earth would be impossible. Emergencies would have to be handled alone. Psychological stress would accumulate without relief. Humans are social beings. Extended isolation changes cognition, emotion, and perception. Confined environments amplify conflict. Uncertainty increases anxiety. Over decades, even the most resilient individuals would struggle. Neptune would not need to harm humans physically. Time would do it. The longer a crew remained isolated, the more fragile their mental state would become. Motivation would fade, decision-making would slow, errors would increase, and at Neptune's distance, errors are fatal. Medical care would be another unsolvable problem. A human mission to Neptune could not rely on evacuation. There would be no return window, no rescue mission. Any serious illness or injury would have to be treated with limited resources. Far from Earth, years away from help, even routine medical procedures would carry heightened risk. Infection control would be difficult. Supplies would be finite. Equipment failures could not be replaced. The human body is adaptable, but it is not immortal. Neptune demands endurance beyond what biology comfortably provides. And then there is gravity. Neptune's gravity is stronger than Earth's. While this might sound manageable, sudden changes in gravitational forces can stress the body. Prolonged exposure to altered gravity environments can affect circulation, balance, and organ function. Combined with years of microgravity during transit, readapting to stronger gravity would be dangerous. The body would struggle to cope. But even if humans could survive the journey, the isolation, the radiation, and the physical strain, Neptune itself would remain untouchable. Humans could not descend into its atmosphere. They could not approach its storms. They could not land or explore directly. Every interaction would be mediated through machines that Neptune is designed by nature to destroy. This creates a paradox. A human mission to Neptune would exist primarily to watch machines fail. That is not exploration in the traditional sense. It is endurance. And endurance without direct reward is psychologically corrosive. Humans need feedback. They need progress. They need the sense that effort produces results. Neptune offers none of that. It offers distance, delay, and destruction. This is why Neptune represents a unique challenge to human ambition. It is not merely far away. It is fundamentally incompatible with human presence. Mars challenges our engineering. Jupiter challenges our radiation shielding. Neptune challenges our biology, psychology, and patience all at once. It is a test not of strength, but of limits. And this realization forces a re-evaluation of what exploration means. Not every place can be visited by humans. Not every world is meant to host life or be walked upon. Some environments exist only to be observed, studied, and respected from afar. Neptune is one of those places. It is not a failure of courage that keeps humans away. It is an understanding of consequence. The farther we push outward, the more the universe reminds us that it does not adjust itself for us. It does not soften its extremes. It does not care about our timelines or ambitions. Neptune stands as a boundary between curiosity and survival. Crossing that boundary with humans would require sacrifices so extreme that the value of the mission becomes questionable. And perhaps that is Neptune's final lesson. That exploration is not about conquering every place. It is about knowing when presence becomes destruction, not of the world being explored, but of the explorers themselves. Neptune does not threaten humans directly. It simply exists in a way that makes human presence impossible. And sometimes, that is the most absolute barrier of all. Neptune forces a conclusion that is difficult to accept. It is not that we cannot reach Neptune. It is that reaching Neptune does not mean we can interact with it in any meaningful way. For centuries, Exploration has been defined by arrival. Reaching a place meant understanding it, setting foot on land, touching soil, building instruments, staying long enough to observe change. Neptune breaks that definition completely. At Neptune, arrival is not access. It is exposure. The moment a spacecraft enters Neptune's domain, the planet begins to act on it. Cold drains energy, radiation degrades systems, winds introduce stress, gravity limits escape, time magnifies every weakness. There is no moment where control increases after arrival. Control only decreases. This changes the role of technology. On Earth and nearby worlds, technology extends our reach. It allows us to survive where our bodies cannot. It buys time. It stabilizes environments. At Neptune, technology does the opposite. It becomes the fragile element. It becomes the first thing to fail. Neptune does not challenge us to build stronger machines. It challenges us to reconsider the idea of machines as explorers. Every additional system adds complexity. Every layer of redundancy adds mass. Every protective measure introduces new failure modes. Neptune exposes this tension mercilessly. A spacecraft designed to survive longer becomes heavier. Heavier spacecraft require more fuel. More fuel increases mission duration. Longer missions increase exposure. The loop closes. The very act of preparing for Neptune makes Neptune harder to survive. This is why Neptune has remained largely untouched since Voyager 2. Not because of lack of interest, but because every proposed mission runs into the same wall. The environment is not just harsh, it is systematically incompatible with sustained presence. Even orbiting Neptune is an act of compromise. To orbit safely, a spacecraft must remain far enough away to avoid atmospheric drag and radiation spikes. But distance reduces resolution. Instruments see less detail. Measurements become indirect. Move closer and data improves, but risk increases sharply. Neptune does not allow both safety and clarity. This forces exploration into a narrow channel. Flybys provide brief glimpses. Remote sensing offers partial answers. Models fill in the gaps. But direct interaction remains elusive, and this limitation has broader implications. Neptune is not unique. It represents an entire class of worlds, ice giants that appear frequently throughout the galaxy. Exoplanet surveys suggest that Neptune-sized planets are among the most common planetary types in the universe. If Neptune is any indication, many of those worlds may be equally hostile. They may look calm from a distance, blue, smooth, serene, but beneath that appearance may lie internal engines driving violent atmospheres, unpredictable magnetic fields, and environments that erase complexity. This realization reframes the search for habitable worlds. It reminds us that appearance is misleading, that size, color, and orbit do not guarantee stability, that planets can exist in states that are long-lived but incompatible with life and exploration. Neptune endures not because it is gentle, but because it is efficient. Its internal heat is trapped and recycled. Its atmosphere converts energy into motion with minimal loss. Its system does not decay quickly. It has found a balance, just not one that includes us. And perhaps that is the deeper lesson Neptune offers. The universe is not optimized for explorers. It is optimized for itself. Planets do not evolve to be visited. They evolve according to physics, chemistry, and time. When those processes produce environments that exclude us, it is not a failure of imagination or ambition. It is a boundary set by nature. Neptune sits at one of those boundaries. It marks the point where curiosity must yield to restraint, where observation must replace interaction, where understanding must come from distance rather than presence. This does not diminish Neptune's importance. It enhances it. Neptune becomes a reminder that exploration is not always about intrusion. Sometimes it is about learning how to observe without interfering, how to infer without touching, how to respect environments that cannot be entered safely. Future missions to Neptune will likely follow this path. Orbiters that stay distant, telescopes that observe from afar, instruments that listen rather than engage. And that may be enough, because Neptune does not need to be conquered to be understood. It needs to be studied on its own terms. Its storms tell stories about planetary heat. Its winds reveal how energy moves without sunlight. Its magnetic field exposes the diversity of planetary interiors. Neptune teaches us that planets can be powerful without being welcoming, stable without being safe, beautiful without being accessible. And in doing so, it challenges a long-standing assumption that every place in the universe is a destination. Some are not. Some are boundaries that define how far exploration can go before it must change form. Neptune is one of those places. It does not invite us closer. It does not reward persistence. It does not respond to effort. It simply exists, operating according to rules that leave no room for us inside them. And perhaps that is the most honest outcome of exploration. Not the triumph of arrival, but the humility of understanding where arrival is no longer the point. Neptune is not a world waiting to be visited. It is a world reminding us that exploration has limits, and that recognizing those limits is not failure, but wisdom. Neptune leaves us with an uncomfortable question. If a planet exists that we can reach, but cannot meaningfully touch, cannot safely orbit for long, cannot descend into, and cannot inhabit, what does exploration mean there? For most of human history, exploration followed a simple pattern. We went somewhere new, observed it directly, adapted to it, and eventually learned how to survive there. Oceans were crossed, continents were mapped, mountains were climbed. Even space exploration has followed this logic, moving step by step from Earth orbit to the Moon, then outward to Mars. Neptune breaks that pattern. It allows approach, but not presence. It allows observation, but not interaction. It allows knowledge, but not occupation. This forces a shift in perspective. At Neptune, exploration stops being about endurance and becomes about interpretation. We are no longer explorers entering a space. We are observers trying to understand a system that does not accommodate us. That distinction matters because many of the assumptions behind exploration, bravery, persistence, adaptation, lose relevance when the environment itself erases complexity faster than it can be sustained. Neptune does not test courage. It tests compatibility. And compatibility is not something that effort can overcome. Neptune's physics do not negotiate. Its winds do not slow because we try harder. Its radiation does not weaken because we shield more. Its distance does not shrink because we plan better. The planet simply continues operating. This realization reshapes how scientists think about the outer solar system. It suggests that there are regions where exploration must rely almost entirely on indirect methods, remote sensing, gravitational measurements, magnetic field analysis, atmospheric spectroscopy. These tools are powerful, but they are limited. They provide fragments, not full pictures. They require interpretation, inference, and modeling. They demand patience. Neptune forces science to slow down. Instead of direct experimentation, we must observe patterns over time. Instead of descent, we must watch from above. Instead of intervention, we must let the system reveal itself gradually. This is frustrating. Human curiosity prefers immediacy. We want to see, to touch, to measure directly. Neptune denies that impulse, but it also teaches something important. Not all knowledge comes from proximity. Some of the most profound discoveries in astronomy come from distance. We learn about stars we will never reach, galaxies we will never visit, phenomena that exist far beyond our physical grasp. Neptune belongs in this category. It is close enough to tempt us, but hostile enough to resist. And that tension makes it valuable, because Neptune becomes a test case for understanding worlds that cannot be entered. Worlds that exist in extreme states where matter behaves differently, energy flows unexpectedly, and familiar concepts lose meaning. Studying Neptune from afar teaches us how to study similar planets elsewhere in the galaxy. Ice giants appear to be common around other stars. Many exoplanets we detect resemble Neptune more than Earth. If Neptune is representative, then much of the universe may be filled with worlds that are active, energetic, and utterly incompatible with life or exploration as we know it. That insight matters. It reshapes the search for habitable worlds. It cautions against assuming that planets in certain size ranges or orbits are benign. It reminds us that internal processes matter as much as distance from a star. Neptune's internal heat, its violent atmosphere, and its unstable magnetic field all arise from processes hidden beneath layers we cannot penetrate. Understanding those processes requires models, not measurements, hypotheses, not experiments. This is where uncertainty becomes permanent. Neptune may never be fully understood. There may always be questions we cannot answer definitively. What exactly powers its internal heat? How does energy move through its interior? Why do its storms behave the way they do? These questions may remain partially open for generations, and that challenges another assumption, that exploration is about closure, that every question has an answer waiting at the destination. Neptune suggests otherwise. Some worlds offer insight without resolution. They reveal patterns without explanations. They expand understanding while preserving mystery. This is not a failure of science. It is a boundary condition. Science advances not only by answering questions, but by discovering which questions cannot be answered with current tools. Neptune defines one such boundary, and perhaps that is its most important role. Neptune stands at the edge of our solar system as a reminder that not all frontiers are meant to be crossed physically. Some exist to teach us restraint, to show us where observation must replace intrusion. In this sense, Neptune is not an enemy of exploration. It is a guide. It tells us where our methods stop working. It shows us how complexity can arise naturally and sustain itself without regard for observers. It forces us to refine our models, improve our instruments, and accept uncertainty as part of understanding. Neptune also humbles us. It reminds us that technological advancement does not grant universal access, that there are environments where even our best machines are temporary visitors, that progress does not erase physical limits, and humility is essential for long-term exploration. As we look beyond Neptune to the Kuiper Belt, to interstellar space, to other star systems, we will encounter many environments like it. Places where direct interaction is impossible, but indirect study is rich with information. Neptune prepares us for that future. It trains us to observe patiently, to infer carefully, to accept that some systems cannot be mastered. And in doing so, it changes the narrative of exploration. The goal is no longer to plant a flag everywhere. The goal becomes understanding without conquest. Neptune does not invite us closer, but it does invite us to think differently, to expand our definition of exploration beyond presence and survival, toward interpretation and insight. And that shift may be essential if humanity is to continue exploring a universe that is far larger, more extreme, and less accommodating than we once imagined. Neptune does not shut the door on exploration. It shows us where the door changes shape, where progress requires patience rather than persistence, where knowledge comes not from touching, but from watching. And that lesson may be more valuable than any data a destroyed spacecraft could ever send back. Neptune does not end the story of exploration. It reframes it after everything we have learned about its winds, its cold, its pressure, its radiation, its distance, its ability to dismantle machines and exclude humans. Neptune forces a final realization that is difficult to ignore. Exploration is not infinite. There are limits that cannot be crossed by determination alone. Limits set not by fear, but by physics. Neptune exists precisely at one of those limits. It is close enough to reach, but far enough to punish every assumption we bring with us. Hostile enough to destroy complexity, yet stable enough to persist unchanged for billions of years. It does not evolve toward accessibility. It does not soften over time. Neptune remains what it is. This challenges a deeply human idea that every unknown place is eventually conquerable. That with enough technology, enough patience, and enough courage, we can go anywhere and survive. Neptune quietly disproves that belief. It shows that some environments are not meant to be entered, not because they are guarded, but because their very nature excludes intrusion. The processes that keep Neptune alive as a planet are the same processes that make it lethal to visitors. Its internal heat must escape. Its atmosphere must move. Its magnetic field must fluctuate. If any of these processes stopped, Neptune would not be Neptune anymore. To make Neptune safe would be to destroy it. And that is an important distinction. Exploration is often framed as overcoming nature. Neptune reveals the cost of that mindset. It teaches that understanding does not require domination, and that presence is not a prerequisite for knowledge. Some truths can only be approached asymptotically, never reached, only inferred. Neptune is one of those truths. This is why future exploration of Neptune will likely be cautious and indirect. Orbiters that remain distant, telescopes that study its atmosphere from afar, instruments that listen to its magnetic field rather than trying to penetrate it. This is not retreat. It is adaptation. It is science learning how to work within limits rather than attempting to erase them. Neptune also prepares us for what lies beyond the solar system. As we discover more exoplanets, we are finding that Neptune-like worlds are common. many planetary systems are dominated by ice giants, worlds with deep atmospheres, internal heat, violent weather, and no solid surface. If Neptune is any guide, then much of the universe may be filled with planets that are active, energetic, and completely incompatible with life or exploration as we imagine it. That realization reshapes the search for meaning in space. It suggests that habitability is rare, not because planets are scarce, but because stability is fragile. It reminds us that Earth's calm is unusual, not typical, that our planet exists in a narrow window of conditions that allow complexity to persist without being erased. Neptune sits outside that window, and in doing so, it highlights how extraordinary Earth truly is. But Neptune is not a warning meant to discourage exploration. It is a lesson meant to refine it. Exploration must become more selective, more observational, more humble. It must accept that some systems are better understood through theory and remote sensing than through direct interaction. This does not make exploration less meaningful. It makes it more honest. Neptune also changes how we think about machines. We often imagine that better materials, smarter software, and stronger structures will eventually allow us to survive anywhere. Neptune shows that complexity itself is a vulnerability, that the more intricate a system becomes, the more ways it can fail in extreme environments. Simplicity survives longer. This is why Neptune favors fundamental physics over engineering. Pressure, temperature, motion, and radiation strip systems down to their essentials. Anything unnecessary is removed. Anything fragile is erased. Neptune does not attack complexity. It filters it. And what remains is whatever can exist without structure, control, or intention. This filtering effect is not unique to Neptune. It is a universal principle. Extreme environments everywhere favor simplicity. Stars favor plasma. Black holes favor nothing at all. Neptune favors motion and pressure. Understanding this helps us place ourselves correctly in the universe. We are not the center. We are not the default. We are a special case. Neptune reminds us of that. It stands as a counterexample to the idea that the universe is gradually opening itself to us. Instead, it shows that the universe is vast, varied, and indifferent. Some regions are accessible, others are not. And that indifference is not hostile, it is neutral. Neptune does not care whether we observe it or not. It does not change its behavior when we look away. It does not respond to curiosity or ambition. It simply continues. That continuity is powerful. It means Neptune will outlast us. It will continue to operate long after our machines fail, long after our questions change, long after our definitions of exploration evolve. Neptune will still be there, cold, violent, active, running its internal engine in silence. And perhaps that is the final lesson Neptune offers. That exploration is not about ownership or conquest, but about perspective, about learning where we fit within a universe that does not bend to us. Neptune shows us that we are visitors, not rulers, observers, not masters, and that understanding may be the most important discovery of all, because as we push farther into space, the question is no longer whether we can reach these worlds. The question is whether we can accept what they tell us when they push back. Neptune pushes back gently, but absolutely. It does not say no loudly. It simply does not say yes. And in that silence, it teaches us the shape of our limits and the kind of exploration that must exist beyond them. That is why Neptune is not just a distant planet. It is a boundary, a mirror, and a reminder that the universe is far stranger, harsher, and more indifferent than we once believed, and that understanding it requires not only technology, but humility. And sometimes, distance is not a barrier to knowledge. It is the only way knowledge is possible.